There are times when you'll place the analyzer on the cabling system and you'll just capture a whole bunch of traffic, and you just need to get a general feel for what kind of traffic was in your trace file. In this case, we can use the statistics protocol hierarchy information. So I'm going to open a trace file. Here we go. I'm going to leave the colorization on. Now I'll go up under statistics and protocol hierarchy. And that gives me a general idea of the traffic that's in that trace file. Now remember that DHCP is also the bootstrap protocol. So we see IP traffic, and then we see some UDP traffic. We also see some TCP traffic. Now under UDP traffic, we can see that we have some, net BIOS stuff. DCE, RPC, Distributed Computing Environment, Remote Procedure Call traffic. Microsoft Messenger service. We also see that we have some net BIOS traffic, and if we're not using net BIOS on the cabling system, we shouldn't see that traffic here. We can see that it's SMB traffic, SMB mail slot protocol traffic, the Windows browser protocol. So this will give you a general idea of what you have. And if you're looking at something like HTTP traffic, it will also break down that HTTP traffic based on the type of data that's contained in the HTTP communications. In addition, it will give you the percentage of the traffic that is that particular protocol, number of packets that each one of those protocols has, the bytes, the megabits per second, the end packets, and the end bytes. That's basically telling you how many packets are the DHCP or BootP packets and how many bytes they use in total, and then the final count in the megabits per second for that entire trace file. So it's a nice look overall at what's going on. Let me show you an example of how you might use this in the case of security. And I'm going to open up a trace file called client dying. Now this is an interesting trace file because it's of a client system that boots up, and it only lasts for about 3 minutes, and then CPU utilization goes to 100% and the system just completely locks up. So what I want to do is I want to see what types of protocols and what types of communications are involved during the boot up sequence. So this is the trace of that boot up sequence. I'm going to select statistics, protocol hierarchy, and here I can see, okay, there's some net BIOS stuff in there that probably shouldn't be in there. There's DCE, RPC stuff in there. Yahoo Messenger protocol is in there. And, maybe we don't want to let our client use Yahoo Messenger, especially during the startup sequence. But then we also see some DCE, RPC traffic running over TCP. So there's TCP up there. And look a little further, we've got IRC. We've got an IRC communication in this trace file. So now we know what we want to look for in here. We want to see what is this IRC traffic. We also see this, which is TFTP. That's Trivial File Transfer Protocol. That's FTP over UDP, which just doesn't feel right on the network. So just by looking at the hierarchy information here, we can get a general idea of what we might want to filter on and what we might want to watch out for in this traffic. I'm still in the client dying.dmp trace file, and now I want to look at conversation information. A conversation is considered a communication between two devices, and we can look at a conversation as an Ethernet conversation between this hardware address and this other hardware address down here. Or we might be looking at it based on the IP layer, a conversation between this IP address and this IP address. Or if we go up through the stacks to a higher layer, we might be looking at TCP conversations, and TCP conversations would be based on a certain IP address talking to another IP address, but also a specific port talking to another port. So we're trying to group together these conversations to look at. So I'm going to select Statistics, Conversations, and that will pull up the main conversation list. Here we can see it shows us that in this trace file we have one Ethernet conversation. There are the two MAC addresses seen in this trace file. We have 13 IP conversations going on, 13 pairs of IP communications going on, 29 TCP conversations going on, and 4 UDP conversations going on. Let's start by looking at the UDP conversations. So I've clicked on the tab, and now it lists the conversations. And as I mentioned before, when you get up to the layer of TCP or UDP, it's not just the IP addresses, which IP addresses are communicating with each other, but it's also the port numbers that they're using to communicate with each other. So here we can see 172.16.1.10 communicating from port 1048 to 172.16.0.254, and port B there would be the DNS port, so that's port 53 that's just been translated over. But if we look at this, there's kind of something weird here. There's that TFTP communication. That's the trivial file transfer protocol communication. And that's the thing that's kind of weird that we didn't want to see in this startup sequence for this client system. Now, when you're in conversations and you see something that's unusual like that, there are several things you can do. First of all, you can right mouse click and you can apply this as a filter. Say, I only want to see that communication. Based on the selected value, I want to see the conversation both directions bidirectionally, or I only want to see the communication that's going from the address A listed up here in the first column to address B, or only things going from the address listed in address B column going to A, or A going to and from anyone, etc. So you have all these options. In addition, you can say, I want to see everything except for this conversation. And then we can do some work with Boolean operands in here as well. Now, here we have the capability of preparing a filter, which means we prepare the filter, but we don't automatically apply it in the background. So if I say I want to prepare a filter based on a conversation, we have the same options here. Remember, a lot of this filtering information is in section 8 of this course. We could also say that we want to find a packet. We want to find a packet, any one of those packets between A and B that have to do with this conversation. So that will take us immediately to that TFTP communication. We can also colorize a conversation, and that will open up the color filter window. So we can build a color rule and say that we want this conversation to be black background with a green foreground or something like that. I'm going to try the find packet option here. Say I want to find a packet, and I'm looking for any packet that's going between A and B. Now that's a combination of the address and the port for A and the address and the port for B. Click on that. There's the filter that it will build to find the packet. Here we go. Say I want to find that. I'll close this window down. And in the background, I'm on packet number 70. And sure enough, packet number 70 is a TFTP communication, the very first TFTP communication in that trace file. So the conversations information is really nice, but you can do more than just look at the information. A lot of people just go in and sort of look at it and say, oh, that's an interesting chart, and I know I can sort. But once you find something interesting, you can go directly to that packet, or you can even colorize it so it shows up better. Now I'm looking over at the TCP conversations that are in that trace file. I'm going to sort according to the bytes column heading, so I have a little arrow pointing up. Now that means that I have the most active conversation showing up on top, and that's based on the byte count. So I can select that specific conversation, right mouse click, and say that I want to apply a filter based on that. Now, in section number 8, we'll go through all the filtering stuff, but this is an easy way of applying a filter. I'll select all traffic to and from A and B based again on the values that you see here in the background, address A, port A, address B, port B. Say OK, and there we go. Now you can see that the filter is automatically placed up there, and we're able to see that that communication is an IRC communication. So besides using statistics just for general the conversation statistics just for general information about the traffic cruising around, IP traffic, TCP traffic, and UDP traffic, we can also pull out a specific communication very easily by just selecting conversation, right mouse clicking, and then either applying filters, preparing filters, finding a packet, or colorizing that packet traffic. Now, endpoints are different than conversations, and I'll show you how. If we open up statistics, conversations, and take a look at the conversations listed in that same trace file that we were working in before, and then we go under statistics and endpoints and pull up the endpoint list, I'll put one on top of the other so you can see the difference between the two. Let me scale this down a little bit so we'll be able to see a little bit more of the background window. So now I've got them one on top of each other, and the top window here I have is the conversations window, and the bottom window I have is the endpoints window. You can see in conversations that we're pairing everything up. So here we see that there's one Ethernet conversation, one pair communicating. But down in the endpoint section, we list everything separately. So each one of the hosts is listed on a separate line based on their Ethernet address here, or their IP address. They'll each be on a separate line. Their TCP port number information that they're using, UDP, the port number information they're using. Each one of the entries will be on a separate line. And I'll show you as another comparison what it looks like when we look at the UDP information. So in the conversations area, I'm just looking at pairs of communications going over UDP. So here we can see 172.16.1.10 communicating through port 1048 with 172.16.0.254, and the port there is the domain port, the DNS port. Now let's look at how that would be listed in the endpoints area. I'll go over to UDP, and here we can see that in UDP communications we have 6 different endpoints. We see 172.16.1.10 using port 3735. We also see 172.16.1.10 using port 1048, 1091, and 1113. Now up above, these are paired with other devices that they're communicating with. So we'll see this 172.16.1.10 communicating with using port 1113, talking with the DNS server. Down below we see that DNS server is listed on its own separate line. And everything that we could do in the conversations area, we can also do in the endpoints area. So if I see something that I'm interested in, there's that TFTP communication, I can right mouse click, and again I can apply a filter based on that communication. I can prepare a filter, which I can apply manually later. I can find a frame, or I can colorize that host traffic. Let's take a look at how we can use the conversations and endpoint information to identify some possible security problems on the network. First of all, I'm going to open a trace file called Nutella single session. Now I know it's a Nutella session going on, but there might be other things happening in the background. So the first thing I'll do is I'll bring up the endpoints window. There we go. And we can see from this that we have 3 Ethernet addresses recognized in the trace file. We've got 82 IP version 4 addresses, and then we've got 324 TCP communications. But if you look at the TCP communications, when we sort based on the byte count, you'll see that the majority of these communications are very small communications, and that's not normal. Usually when we make a TCP connection to another device somewhere, we'll have a fair amount of traffic flowing over that connection, so it seems kind of weird right there. If we go over to the area of IPv4 and we sort according to the transmit bytes, we want to see who transmitted the most packets in the whole entire trace file. And here we have 10.1.4.176. And let's just pull out traffic that's associated with that particular IP device. So I build a filter to say, filter on the selected value. It'll apply the filter in the background there. We can look at this traffic for a little more information. We can see that 10.1.4.176 is sending a SYN packet out to this other address. Then we see 10.1.4.176 again sending another SYN packet out at using a different port number. Starting to get these resets back, and it keeps sending all of these SYN packets out. Look at all these SYN packets going out. All these different handshake packets. And when we see something like this, it seems really strange. And it also seems really strange because Wireshark doesn't recognize and doesn't put in what the protocol is at this point. But remember, so far this is just a handshake. We can't make any assumptions as to what protocol this person is using or what application they're using yet. This is only a handshake process. We have no commands to base this on. But as we scroll down, look at all those SYN packets. That's something we just really shouldn't see on the cabling system. So I'm going to clear out that filter, and now I'm going to look at the conversations. So I'll go up to Statistics and Conversations. Now here we go. We can see there's our pair of addresses communicating. So we can see it looks like we have communications between 2 Cisco devices on the network. There's our IP traffic. Those are our pairs, our conversations there. And then here are our conversations in the TCP area. Now I want to pull out the TCP communications where we have the most bytes exchanged. So I'm going to double click on the bytes column heading so the arrow is pointed up. I can see that I have communication up there at the top. Still not that many bytes, but we'll go ahead and pull that one out by right mouse clicking and applying a filter on the selected bidirectional communications. And there we go. We can see that we've got a handshake process. Really isn't a lot in the way of packets, but it came up to the top of the list in bytes transferred because the majority of this traffic was discovery traffic in this trace file. It wasn't actual connections and making transfers type of traffic. We can see there's the three-way handshake, and there's the Gnutella protocol showing up now, because Wireshark recognizes that we really don't know what it is until we see actual data transfer across the wire. Interestingly enough, port number 6346 is associated with Gnutella. So we can see the request to get a file that starts with sorority sex kitten or something like that. There's the acknowledgement coming down, and there's the rest of the request. Now, one last thing I want to show you is how you can extract the information that's shown in the conversations and endpoints chart. Here we're looking at that conversations listing, and we've sorted according to the transmit bytes column heading. Now at this point there's no print, there's no export button or anything like that on this window, but there is a huge copy button, and you can click that copy button, and now that's just copied it into the clipboard. And now we can toggle over to WordPad, and we can paste this into WordPad. You can see that it comes in a comma-separated format. So it would make a lot of sense to put it into some sort of a spreadsheet program where it'll separate all these out in the proper column, so you'll end up with a nice chart that goes with your information. We can also look at destination information in Wireshark. So here I've opened up a trace file which is called pl-zipdownload.pcap. And I'll select statistics and destinations. Now I can apply a filter if I wish at this point, because maybe I'm only interested in the destinations that support DHCP traffic. I only want to see who's talking DHCP traffic or just DNS traffic. If I don't put anything in this area at all, I can just create the statistic on it, wait a moment, and all of a sudden it will populate, and there we go. These are the destinations seen in this trace file. So here we can see 73.68.136.1, and we can click to open up and expand each one of these entries separately if we want to know more information. So we can see that 67.180.72.131 is communicating over UDP and TCP. So we'll open up and see what port it's using for UDP. So we can see port 53. This is obviously a DNS server. And we can see in TCP it's using port 80. So it also supports some web services. Now a lot of times you may be interested in only a specific protocol. So in the filter area, let's just put DNS. And we'll say we want to create the statistic. Give it a moment, and there you go. So we can see that 67.180.72.131 communicating over UDP using port 53, and these other devices are talking to port 53 on this DNS server. So these are the folks that are making DNS queries in the trace file. We'll take another look at a statistic by putting in HTTP and creating the statistic. And here we can see that we've got the 67.180.72.131, and we can see that it's TCP communication port 80. And we can see that this IP address here is associated with TCP communications. And from that system, we can see all these different ports opened up. So that feels like a client system. That's what a client system looks like. We'll go to the last one here and open that one up. And here we can see we only have one port, but it's a client port. It's not like a service port that we would recognize, like a port 80 or a port 110 or port 25 or something like that. So this is most likely a client as well. And one thing you may have noticed when we were on those last screens, we were going into statistics and looking at destinations, is that we didn't see the broadcast address listed there. So let me just open that up. I'm not going to create any filter on that. I'll let it populate, and there we go. You'll see that even though we do have we have DHCP broadcast in the background, that doesn't show up in the destinations area. The way we would see that information is by selecting statistics and IP address. Now again, we have the ability to select a filter. I'm not going to place any filter in here. I'm just going to create the statistic. And here we go. Now we can see that 255.255.255.255 does show up. And when we're looking at this information, we can see the count. Total count of packets is 613, and we can see that down below in the status line. We can see it's total of 613. We can see that the majority of packets have 67.180.72.131 in either the source or the destination IP address field. So 94.94% have this address, either the source or destination address field, whereas 90.21% of the packets have 128.241.194.25 in the source or destination address field. And that's how those count out there. Now, one thing we didn't do is we didn't place any sort of a filter on there. So let's go back and place a filter for DHCP traffic. Again, we can't use DHCP because that's not going to be recognized. We have to type in boot P, and we'll create the statistic. And there we go. So we see that out of the DHCP traffic, 100% of the traffic in there has 73.68.136.1 in the source or destination IP address field. And 100% of the traffic also has the broadcast address in what should be the destination field, because broadcast should never be in the source IP address field. Now let's take a look at the packet length statistics that you can get with Wireshark. I'm still in this PL zip download, which is somebody just basically downloading a zip file off of a website. I'll select statistics and packet length. And again, you can place a filter on this if you're only interested in the packet length of DNS packets or packet length of HTTP communications. You could place the filter in there. But I'm just going to select Create Statistic, and there we go. Now this may look really weird, but let me explain what's happening here. The majority of the traffic is little itty bitty tiny packets between 40 and 79 bytes. 59.22% of the traffic is between 40 bytes and 79 bytes long. The next highest percentage that we see is 18.43% of the traffic that falls between 1280 and 2559. Now we should see packets of 1518 bytes on an Ethernet network. But a lot of times what you'll see is on an Ethernet network, when someone's doing a file transfer, you'll see this listing right here, the 1280 to the 2559, as a high number. The top two numbers should be this one right here. And also you'll see this minimum size packet area, the 40 to 79 byte length packet. And the reason is because these packets up here contain data. These packets down here are probably just ACK packets, just acknowledgement packets, which are minimum sized packets, 64 byte packets on an Ethernet network. I'm going to open up another trace file, and this next trace file that I'm going to open up contains a file transfer, but it's a really large file transfer. And I think that will illustrate even further how those packet lengths work for a file transfer process. So I'll select Statistics. I'm now in this trace file called download-good. And I'll go to Statistics and Packet Length. I'm going to go ahead and create the statistic and I'm not placing any filter on it. There we go. This is typical of what you'll see. The majority of the traffic sits within the 1280 to 2559 and the 40 to 79 range. These are going to be all the ACK packets in that trace file, whereas these higher numbers here should actually contain data in them as they're crossing the wire. Now we'll take a look at the port types statistic area. And it's a little different than you might think. You might think that the port types will give you the list of all the ports that are in use, over TCP or UDP, but it's not. Now, I've opened up a trace file called bittorrent-launch-search-Madonna. So this is somebody looking for a Madonna music file or something using BitTorrent. I'll select statistics, and way down towards the bottom you'll see port type. Select that, and I'm not going to place any sort of a filter on this. I'm just going to say go ahead and create the statistic. I'll wait for a moment and let it populate, and there it is. Now the way that we interpret this is that there are 30 packets that are going to a communication to a port that sits on top of a UDP header. And in this trace file there are 233 packets that are communicating with a port that resides above a TCP header. And strangely enough, we have one packet that does not use a UDP header or a TCP header. So that's how we interpret it. And let's go see what that other type of a packet is. I'll close this window down and close this window down. And now I'm going to create a filter that says I don't want to see any packets that use TCP, and I also don't want to see any packets that use UDP. And I'll hit enter, and that's what we're left with. That's our unique packet that does not use a TCP header or a UDP header. It's IGMP, the Internet Group Management Protocol. And you can see just from the collapsed view in this middle pane that we have an Ethernet header, an IP header, and then we go directly to IGMP. Multicasting is the process of sending packets to multiple devices, as opposed to unicast, which is where we send packets to a single device, or broadcast, where we send it to all devices. Now, Wireshark will actually look down at the MAC address, the destination MAC address field, to figure out whether the packet is a multicast packet. All of this traffic right here that I'm looking at is multicast traffic, and it comes from a trace file called video_multicast.cap that's available on the Wireshark wiki page. Let's go down inside of the packets and I'll show you what designates a packet as a multicast packet. I'm opening up the Ethernet header inside of the middle detail decode window. And we can see that the destination MAC address is 01005E, which is a starting MAC address of a multicast packet. It's kind of interesting because the next 3 bytes of the destination MAC address are gathered by looking at the destination IP address. The destination IP address, the decimal value 111, is equal to the hex value 6F. And the next byte there of 1 is equal to the hex value of 01, and the last destination IP address byte of 03 gives us the last byte of the destination MAC address. But you'll see the beginning bytes start with this 01005E. Now we can even open that up further, and I can show you there's the multicast bit in the packet. If that bit in the IP packet, if that bit in the Ethernet header of the IP packet, I should say, is set to a 1, then we know this is going to be a multicast or a broadcast packet. I'll close this up, and we can see that I have a lot of different destination multicast addresses in here. Now in Wireshark, under Statistics, we can look at our multicast stream statistics. Now it's going to pick up the traffic based on that multicast address. Another thing you should know is that in the world of IP, destination addresses that start with the number 224 all the way up through 239 are going to be multicast packets. I'll bring this window up, And now it's only pulled the multicast traffic out of the trace. If you have a trace that has some multicast traffic, some unicast, or some broadcast traffic, the multicast streams statistic is only going to pull up your multicast streams out of that whole entire trace. So here we can see the source IP address column. And we've got one kind of a strange stream that doesn't seem to match the other ones. We've got a source port column. Again, there's a port that doesn't really seem to match the other ones as well. Then we have the destination IP address column. We've got the destination port column. We've got the total packet count for each of those. And we can sort these columns. So here we can see we brought up the multicast stream that has the highest number of packets associated with it. It's also the stream that has the highest packets per second rate at 539 packets per second. I'll scroll to the right now. We were just looking at packets per second. There's the average bandwidth required for that stream. So 5.9 megabits per second required for that stream. Now that's just the average, and this column gives us the maximum bandwidth per second. So we can get a feel as we analyze multicast streams how much bandwidth each one of those streams is going to require, and then we can multiply that out by the number of streams that we want to support. This is kind of an interesting trace because the maximum number of packets does not match the maximum bandwidth. So here we can see that first stream at 8 megabits per second maximum bandwidth, but the maximum bandwidth of the third stream, it went all the way up to 9.2 megabits per second. So it was a much greater bursty moment that it had. Now the maximum burst is figured out by looking at a window of time. And the window of time, which is called the burst interval, on my system is set at 100 milliseconds. So the maximum burst that it hit was 74 packets within 100 milliseconds. Here we can see one that hit 85. So remember we were looking at that one before, that one had a greater burst, but on average it seemed to be lower on the average bandwidth usage. So in order for it to get up to a burst like that, we must have had 85 packets within a 100 millisecond window of time. The burst alarms column tells us how many times the burst alarms have gone off for that particular stream. So here we can see one where the burst alarm went off 132 times. Now the burst alarm on my system is set at 50 packets per second. So that means that this communication that I'm looking at, and I'll scroll to the left-hand side so we can see some addresses to go with this. This communication going to the multicast address of 227.111.1.6 went above the burst alarm setting 132 times, but the maximum burst was 61. So that means it just barely went above the threshold. Whereas some of these went way above the threshold. There's one that, 85 packets within 100 milliseconds. And that burst alarm was triggered 90 times. So here we had much greater spikes, but not quite as often. Let me scroll to the right. The maximum buffer size tells us how big an output queue should be so that no packets will be dropped within a specified speed. So that can be used for configuring interconnecting devices on the network. The buffer alarms tells us how many times this was not the case. In other words, how many times did we not have enough buffer space and we had to start dropping packets. Now besides giving you the statistics on your multicast traffic, you have some settings that you can define. And the settings are listed on the bottom of this screen. We have the burst interval, which is 100 milliseconds. We can see that. The burst alarm that I mentioned was 50 packets per second. And the buffer alarm, which is in bytes. How many bytes? So I have 10,000 bytes. I'm going to go to the set parameters area. And here are the parameters that I have set for analyzing multicast traffic on my system. There we see our burst measurement and interval. And remember, this is sort of like a window. We're going to look at 100 milliseconds in time, and then we're going to measure how many packets and how many bytes go through that interval. And these next two alarm settings are based on the interval. So 50 packets per second or 10,000 bytes per second would trigger an alarm. We also have the ability to look at things such as emptying the stream at a certain level. And you'll learn more about multicast traffic and multicast analysis in the Wireshark University TCP/IP analysis course. I'll close this window down now. And on the bottom of this area, you also have a button that says Prepare a Stream. So if I simply click on this button, select a stream, and then click on this button, I can easily prepare a filter based on that stream value. So here in the background, we can see that the filter has been placed on the traffic. Multicasting is really nice. The only problem is when multicast gets out of control, because on video multicast, I mean, you've got a lot of bandwidth required by video multicasting. If we're going to just one user, that's one thing, but when we start multicasting it through the network, then a lot of people begin to feel the effects of the multicast traffic. Now it's time for you to test yourself on statistics. You can print Appendix A, which is the Wireshark Lab Exercises Appendix, and follow along with these steps that way. In step number 1, I want you to open up a trace file called bit-torrent-startup-background.pcap. Look into this trace file and determine the elapsed time in the entire trace. In step number 3, I want you to identify which transport protocol is seen more often in this trace, TCP or UDP. In step number 4, I want you to determine which way data is flowing in the most active UDP communication seen in the trace. In step number 5, you'll need to identify the application that is used for the most active TCP communication. And then finally, in step number 6, you'll be looking at the multicast traffic information to determine if we need to provide additional buffer space for that traffic. Now would be a good time to pause the video and complete the lab. When you're ready to watch me go through the lab and provide the answers, restart the video. All right, the first thing I'm going to do is open up that trace file, which is called bit-torrent-startup-background. It's a pretty large file, so I'm going to have to give it a moment to start up. And once it starts up, I want to look first at the summary information. Now, there are a couple of ways of getting the elapsed time in the trace. We can use the time column if we have it set properly. That would be if we have the time column set to show us seconds since the beginning of the packet capture, but that's not the way my system is set up. Fastest way to do this is just to go to Statistics Summary, and we see the elapsed time of the trace is 5 minutes and 43 seconds. Now, as far as which transport is used most often in the trace, I can go into Statistics and my protocol hierarchy to find out that information. And this is always interesting because if you're not sure what protocols are running on the cabling system as you're capturing, you can pull up this window and you can easily see what's out there. Obviously, I've got some things I don't want. I see messenger service on there, and I wouldn't want messenger service on the network. Now here we can see user datagram protocol hits 99.72%, and we can collapse these a little bit so that we can see this a little more clearly. TCP traffic only accounts for 0.20% of the traffic. I'll close that window down. The next question is, which way is the data flowing in the most active UDP communication? So because it's asking me which way it's flowing, that sounds like a conversation. I'm looking at pairs of devices communicating, so I'll go under Statistics, Conversations. And here we go. Now I'm interested in the UDP traffic. So I'm going to sort. And now, as far as which way is data flowing in the most active communication, active based on packets or active based on bytes? You have to kind of watch out for that one. It just happens in this trace file, the most active is both the highest byte count and it's also the highest packet count, both of those. Which way is data flowing? Well, we have no data going from address A to address B. We have no bytes, obviously, either. But all of the traffic seems to be flowing from address B to address A. So it's coming from 24.4.97.251 going to address A. What application is used for the most active TCP communication? Well, we'll go over to TCP. And again, most active based on what? Luckily, our highest packet count is also our highest byte count. So we can see that first line there. Looks like it's HTTP traffic. Do we need to allot additional buffer space for multicast traffic? Well, in this case, we're going to pull up the multicast streams statistic window. Now remember that although if you look through this trace, there are actually two multicast communications in there. One is IGMP though, which is the Internet Group Management Protocol. And multicast streams will pull up the data multicast streams, the ones where we're actually exchanging data. So here I can see there we have source IP address, destination IP address, same source and destination port, which is kind of nice. It'll help us identify what application that is if we need to. The packets, there are only 8 packets in that 5-minute 43-second trace. Average bandwidth is all the way down to 0 megabits per second. Maximum burst, 1 burst in 100 milliseconds. So I don't think that we're going to have to worry too much about that buffer and hitting burst alarms in this trace.